Hello and welcome to this lecture. So, we are going to start studying linear transformations more closely. So, if you remember from our lectures for R2, we were looking at the range of a linear transformation and null of a linear transformation, and that gave us a lot of information about what the linear transformation is. So, that is what we are going to do now. Okay, so, let us say we have a linear transformation T from Fn to Fm. I am going to define the range and null. So, it's good to sort of roughly picture in your head. I mean, I know visualization is really hard when you go to larger N and M, but it's good to have these kind of egg-shaped pictures in your head. So, you think of Fn as this big egg-shaped object, right? Of course, it's not as simple as that, but let's say all the vectors of Fn are inside this egg-shaped object, and you think of Fm as similarly another egg-shaped object. In particular, these will have zeros, like there are 0 vector will also be here, there will be a 0 vector here, right? So, for instance, you can show that any linear transformation will take 0 to 0. It has to happen that way, right? So, these are things you can prove. Think about how you may prove it. So, you can show these things, and all of these things will be useful. I think we showed it in the R2 case, if I am not wrong. Okay. So, what is range? Range of a linear transformation T is the set of all outputs you will get over all possible inputs. You give all possible inputs, collect all the outputs together. What you get is the range of the linear transformation T. Okay. So, even though we say Fn to Fm, input is in Fn, output is in Fm, maybe not all the outputs are reached, maybe only some outputs are reached by some T. For instance, my transformation may assign everything to 0, in which case I will not hit anything other than 0. So, all these are things I can do. It depends on how I specify my output vectors for my basis, right? I can specify all my output vectors to be 0. If I do that, I will only get 0, right? So, I may not cover the entire Fm through the transformation. Okay. So, what I cover is called the range, what I can reach is called the range. Okay. So, this is a picture to keep in mind. So, this entire Fn will go to some part of Fm which is called the range. Maybe it is the entire Fm, okay, maybe it will hit everything, right, but it may not, right. So, in general it will look like this, it could hit the entire Fm. So, in this case this range of T may expand to the whole of Fm also, keep that in mind. I am just doing an illustrative picture here where this Fn goes to this range T. Okay, of course, 0 will be inside the range T, right. So, if you put the input coordinates as 0, definitely the output coordinates are coming out as 0, right. You can see that because 0 times everything is 0. So, you get 0 here. So, the 0 will also be inside the range. So, this is range. Okay. Similarly, there is a very interesting little object here which is called the null of T. This is the set of all inputs which result in 0 output. Okay. What are all the inputs here which are going to give me a 0, origin as the output here. So, that is the null definition, and that also you can denote like this. So, this is a good picture to sort of keep in your mind. Okay. Null is inside Fn, okay, this red colored object here, and under T, the transform T will take everything in null to 0 in Fn. Okay. Now, the transform T takes the entire Fn to range and then entire null to just the origin 0. Okay, this is shown as a red dot here. It's illustrations, but hopefully you can see how this is working. Okay. So, what kind of objects are these null T, range T? Can we study them? If we study them, we learn a lot more about the linear transform T, right. So, that is what we are going to do next. Let us see. First of all, here is interesting result. It turns out range T is a subspace of Fm. It is not just any set, it has to be a subspace, right. So, subspace we know is spanned by a basis, we can study it very, very well. So, range T is a subspace. Similarly, null T is also a subspace, but it is a subspace of Fn, right. Remember, null T is inside Fn, range T is inside Fm. Okay. So, this null T is a subspace of Fn, not just any set, but it is a subspace. Similarly, range T is also a subspace of Fm. Okay, the proof of these facts are quite easy. I am not going to talk too much about it. I will let you read it in your own time. You can just show that basically linear transformations are conserved by inside both null T and range T. If you take two things in range, do a linear transformation, you will stay inside range. You take two things in null, do a linear combination, you will reside inside null. Okay, that is what you have to show that these two are subspaces, and that can be done quite easily. Okay. So, clearly once you know that these are subspaces, I have to try and find their basis and find the dimension, right. Once I know the basis and dimension, I get a sense of what is going on. Okay. So, notice what is happening here. Think about one more step, right. If I say null has dimension 2 or something, my linear transformation is making that 2-dimensional object as a 0-dimensional object. So, it is killing dimension, it is reducing dimension, right. So, if you remember, we always think of these linear transformations in terms of dimensions. How many input dimensions are there? How many does it reduce down to 0? How many does it keep in some sense? Okay, so this dimension view of linear transformation is very important, and this picture gives you that good idea, right? So, maybe null may be nothing, null may only be the origin. If the null is only the origin and the FM is going entirely to FM, maybe the dimension change is a bit different. So, understanding linear transformation in terms of what it is doing to dimensions and subspaces is very important. In particular, the null subspace you have to study very well, because it is sending the null subspace to 0, and then the other subspaces are going, other parts of Fn outside of null are going to the range. Okay, so that is the way to picture this, and let us study this range and null very well, and we should be able to compute the basis, compute the dimension given the matrix, right. So, that will be our next few objectives. Okay. So, first we will start with range. Okay, how to, this range is also called column space, and this notion of rank is also associated with the range. So, let us see all of that next. So, we have, once again we have this transformation T which takes you from Fn to Fm, and there is a matrix of this with respect to, let us say, the canonical basis. The basis itself does not matter, but just for being specific we will take it as canonical basis. This is the matrix, this is the M cross N matrix. You remember what this matrix is, right? The first column is T of E1, the second column is T of E2, so on, right, in canonical coordinates. Okay. Now, the coordinates of vectors in range T, supposing I look at all the vectors in range T, what will be the coordinates? I take arbitrary B1 to Bn from the field F, and then do scalar multiplication and addition, basically linear combination with those coefficients with the columns of M. As I vary all Bi over all possible values in F, I get all possible output coordinate vectors. Basically, I get everything in the range. Okay, so this basically is the range, right? Range coordinates in some sense. Okay, so this you can easily see, we have seen before, this is nothing but the span of the columns of M, right? It's very easy to see. This is basically definition of linear span, right? The span of all the columns of M is nothing but the coordinates of the range of T. Okay, so this is also called the column space. So that's why the range of a linear transformation and the column space of the associated matrix are one and the same in some sense up to coordinates. Okay, so that's what the range is. Range of a linear transformation is also sort of the same as the column space of the matrix associated with the linear transformation. Okay, so now once I say span of columns, we are in familiar territory, right? I have a spanning set for my subspace. Once I have a spanning set for my subspace, I know how to find a basis. I can find a simplified basis. I'll use elimination. I find a reduced form for the basis, so that I get a very good idea of what that column space is or what the range is. In particular, I can definitely find the basis. I can eliminate columns of M. I start with the columns of M and I eliminate. I find a basis for the column space, basis for the range. We've seen enough examples of this. I don't have to talk about this too much. Okay. In particular, the dimension of the range of T, okay, which we will also see later, is the same as the maximum number of linearly independent columns of M. Okay, the dimension of this range T, dimension of the column space, right? When you eliminate, how many pivots you get, right? When you eliminate, some of the rows may become 0. You will have a number of non-zero rows. How many linearly independent vectors are there? That number is called the rank of T or the rank of M. Okay. The rank of the matrix or the rank of the linear transformation is nothing but the dimension of the range of T. Okay. So, it gives you a certain idea, right? The range of T is all the values you get as the output. How big is it in some sense, right? How many dimensions does it have? That gives you an idea of, that gives you the definition of rank. Okay. So, you can see examples here. I've put out 3 matrices, and I'm not going to work this out because we've already seen working out of this. How do you find the rank and how do you do simplified basis for the column space? Take the columns, okay, take the columns, think of them as rows, put them down below, you just eliminate, same thing, find pivot, make everything pivot 0, then do column swap, row swap if you like, and then make a non-zero pivot. That's it. The same process. You will get the number of linearly independent vectors as the rank, and the basis itself will also come. You may have to do swaps to make sure that you respect the positioning correctly. Okay, so I'm not going to work out these examples. These are examples that you can very readily work out. Okay, so that concludes this very short lecture on range and a basic introduction to linear transformation. We'll proceed by studying null spaces and all of that in the next lecture. Thank you very much.